Assalamualaikum to Dr. Aizudin Supee and my fellow friends. So we are from group 2. We'll present our lab report of the experiment vapor compression refrigerator. These are our team members. The first one is Fakhrul Rasyid. The second one is Mohamad Hanis, followed by Ahmad, Lukman, Aqil, and myself, Afina Ainna. For introduction, the vapor compression refrigeration cycle is a method that uses refrigerants in their liquid and gaseous states to do cooling, which is absorb and release heat. And also, when cooling happens, the heat is transferred from a low temperature area to a high temperature area. So this system consists of four main components. First one is the compressor, condenser, expansion valve, and also evaporator. So this experiment also teaches us on how it applies in real life, real world applications, such as for climate control, we have the AC aircon. For food preservation, we have the refrigerator, and also for industrial processes. Example for industrial processes is when the LPG need to be stored or transport, it needs to be cooled until negative 162 degrees Celsius. Okay, the objective of this experiment is to determine the coefficient of performance, COP, for vapor compression cooling system, which this also determine the efficiency of the cooling of the refrigerator. The theory for these experiments involve the first and the second law of thermodynamics, which basically the first law of thermodynamics explain about the energy conservation, which energy cannot be created or deleted, but it can transfer from one form to another. So the second law of thermodynamics, it explains about the entropy, which the heat goes against its natural direction. So it happens when cooling process happen, the heat is moving from cold region to a hot region. The next one is, as I mentioned before, about the vapor compression refrigeration cycle. It involves four components. So the first one is the evaporator, which it happens, the refrigerant absorbs heat from its surrounding, causing it to evaporate. So the second one, in compressor, the low pressure gas is compressed, increasing its pressure and temperature. The third one is in the condenser, the high temperature gas releases heat to the environment and condenses back into high pressure liquid. And the last one is the expansion valve. The refrigerant's pressure drops suddenly, cooling it down and making it ready to absorb heat again in the evaporator. Next is the coefficient of performance. So by calculating this, we can know about the efficiency of the refrigerator. So the COP is calculated as the ratio of the heat absorbed by the refrigerant in the evaporator to the work input from the compressor. So the formula we use is the COP equals to Q2 over, in bracket, Q1 minus Q2, which the Q1 is the condenser and the Q2 is the evaporator.
Hi and Assalamualaikum. My name is Ahmad Lukman Aqil, and today I will handle the part about the apparatus. What we have here is the vapor compression refrigeration. As you can see on the both side, there is a pressure gauge. In the middle, there is a main valve, and at the bottom of the left, there is an expansion valve. In this experiment, there will be a several reading about the temperature. The four reading you can read by looking at the digital screen that are located on the top of the apparatus, while the other three you have to read by your own on the thermometer. There is also the flow meter on the both side. At the top of the flow meter, where the control valve is located. The next part is methodology. Step 1, you have to open the main valve by rotating anti-clockwise, similar to the step 2 by you open the expansion valve on the anti-clockwise. Step 3, open the water pipe, also an anti-clockwise rotation. On step 4, you have to set the water flow rate to the evaporator as 25 gram per second. And on the water flow rate on the condenser, you have to max out. On the step 5, you have to switch on the main switch. Step 6, allow the cooling system to be stable approximately 10 minutes. After that, record the all parameters, which is pressure gauge and the temperature, in the table given. Step 8, repeat the experiment by changing the flow rate of water to the condenser in between 35 to 40 gram per second. Repeat this experiment 4 times. At the end of experiment, to conclude it, you have to switch off the main switch. Step 10, after switch off the main switch, you have to wait for 1 minute for system to cool down. After that, turn off the water supply pipes by clockwise rotation. Same goes to the step 11, close the main valve, and then step 12, close the expansion valve. The next part is safety procedures. First, you have to wear appropriate personal protective equipment, including lab coat, closed toe shoes, and glove if necessary. Second, avoid loose clothing and jewelry that could get caught in equipment. And if you have long hair, you have to tie it. Third, do not horse around and keep the workspace clear of unnecessary items which can cause tripping. Fourth, make when you want to take data, make sure the eyes are in line with the liquid column or digital screen to avoid parallax error and obtain an accurate reading.
My name is Mohamad Hanis and I will present about data and calculation. During the experiment was conducted, there were some parameters that were recorded to justify the experiment. As we can see the value in the table given in the slide. For rate of heat transfer at condenser and evaporator, then coefficient of performance COP, we need to calculate by using formula. The formula of heat transfer at condenser is Q equal to M1 bracket H4 minus H3, while the formula of heat transfer at evaporator is Q equal to M2 bracket H2 minus H1. We can get enthalpy H1 by interpolation at T1 using steam table at saturated liquid. Same goes with H4. Next, we can get enthalpy H2 by interpolation at T2 using steam table at saturated vapor. We use same method for H3. After that, we can calculate the COP by using the formula modulus Q evaporator over Q condenser minus Q evaporator. As we can see, for the value of COP, test 1 is 0.3837, test 2 0.3959, test 3 is 0.4024, for test 4 is 0.4089, and lastly test 5 is 0.4157. The coefficient of performance COP increase since the rate of heat transfer is different. We can conclude that COP is directly proportional to the rate of heat transfer in the evaporator and inversely proportional to the net outward.
Okay, thank you, Hanis, for the explanation. So, as we can see from the table from the previous slide, we can now answer the discussion. Calculate the rate of heat transferred across in the evaporator in the condenser for the 5 test run and discuss the result. So, as mentioned by Hanis, one of my groupmates, the rate of heat transfer in the evaporator is increasing from test 1 to 5 and the value is always positive after test 1. So what we can conclude here, it is because the heat is absorbed in the evaporator based on the vapor compression refrigeration system diagram. Since the absolute condenser is varied, the rate of heat transfer in the condenser is different, which decrease from test 1 to test 2 and increase after test 2. So the secondly, negative value is also obtained because heat absorbed by the condenser. So the COP or the coefficient of performance increase since the rate of heat transfer is different. It can be concluded that the COP and the rate is dependent and the COP is directly proportional to the rate of heat transfer in the evaporator and inversely proportional to the net of work, which is the difference between the rate of heat transfer in the evaporator and the rate of heat transfer in the condenser. The closer the COP to the value 1 indicates better performance. That's all from me. Thank you. Okay, so right now we're gonna go to second part of our discussion, which is required us to draw a graph of compressor power input watt against the condenser flow rate kilogram per second. As we can see from the graph, it is uniformly increased. Why this happen? Okay, first of all, we can see that the initial increase at low condenser flow rate. As the flow rate increases, the compressor power may initially increase due to need to compress the refrigerator more as the heat exchange efficiency improves. So, what are the key factors in influencing the graph? There are four key factors, which is the refrigerant type. So, different refrigerant have varying thermodynamic properties affecting power return. And the second of all will be the system efficiency. The efficiency of the heat exchanger and compressor affects how power consumption changes with flow rate. We have the ambient condition, which is the variation in temperature and pressure condition can impact performance. And last but not least, the operating point. So different operating point will shift the curve. So what we can conclude from the graph is that the exact shape of the graph will depend on the specific parameters of the system, including design, refrigerant properties, and environmental conditions. A typical graph may resemble an upward slope with a tendency to plateau as the flow rate increases. That's all for me. We're gonna go to the next part, which is the conclusion. Okay, so what we can conclude from the experiment. So from the experiment itself, the experiment 3 refrigeration cycle, we know that a liquid refrigerant is cycled through 4 stages in a closed system as part of the refrigeration cycle. So there are 4 main parts, which is the evaporator, the compressor, the condenser, and also the expansion valve. So what is the function of each of the main components in refrigeration cycle? We have evaporator, the refrigerant absorbs heat from its surrounding, causing it to evaporate. The compressor, the low pressure gas is compressed, increasing its pressure and temperature. Condenser, the high temperature gas release heat to the environment and condense back into a high pressure liquid. And the expansion valve, the refrigerant's pressure drops suddenly, cooling it down and making it ready to absorb heat again in the evaporator. So what is the purpose of the experiment so that we can get the COP? What is COP? As mentioned from my roommate, Afina, in the previous slide, COP is calculated as the ratio of heat absorbed by the refrigerant in the evaporator cooling effect to the work input from the compressor it serves as a measure of the refrigeration system efficiency. So how can we get the COP, desired result of a required input? So we can conclude that COP, we want to find the cooling effect and also the work done on the system. So from the experiment itself, we have achieved the objective of the experiment because we have increased the load. All components of the refrigeration cycle were affected. The parameters such as pressure, enthalpy, and temperature and the four states of the refrigeration cycle were determined and calculated. This enabled us to calculate the COP, as I mentioned just now, and the efficiency of the refrigeration cycle. As discussed before, uh, I think that's all from me. Thank you. Okay, so we're gonna go to the last part of our presentation or the last part of our net report. The references that we get before and after we do the experiment. First of all, we have the YouTube video and doctor can click on the link. And second of all is the slideshare.net about it shows the information about our experiment. And third reference is the calculation, the COP and so on we get from Chengel Yunus a thermodynamics and engineering approach, Boston, McGraw Hill higher education. And last but not least, also the link to the experiment also, so that we get more information about it, is from the textbook of Vapor Compression Engineering. That's all from me. Thank you. Alright, that's all from us. I would like to take this opportunity to represent all my group mates, Afina, Hanis, and also Lukman, for giving us the opportunity to representing experiment 3, vapor compression refrigeration, and I hope that everyone well and understand what we want to explain. That's all from us. Thank you.